Good morning to everyone. Good morning. Okay, done. Very good morning. Okay, so what I will do is, as usual, I will discuss whatever we have discussed in the last class before going for the today's concept. Okay, so in the last class we have discussed a very important one is that is related to aquaresia. Right? So what do you mean by aquaresia? Any one of you? Any one of you can tell me what do you mean by aquaresia? Okay, good morning. Fine. So what do you mean by aquaresia? Aquaresia means royal water. That is where there will be a combination of HCl and HNO3, right? So that's where we have the aquaresia. Yes, Vivek, very good. So that's where we have the 3:1 ratio, right? So now all of you have observed, or all of us we have studied. When I am talking about aquaresia, they are called as royal water. That is because why they are called as royal water? Because they have the capacity to dissolve royal metals like gold, platinum and all, right? So these are the least reactive metals, but when I am taking this one in combination, alone they cannot, but when in combination of 3:1, they have the capacity. Amit, you have written 1:3, then it becomes HNO3 is to HCl, okay? So that's where we have the aquaresia, where it will convert gold into, it will convert gold into oro tetrafluoride, right? And platinum, it will convert platinum into hexafluoride. So platinum hexafluoride, that's where we have the conversion. So that means whatever solid form is there, whatever solid form is there, they are getting converted into aqueous form. That's where we have the aquaresia, which can solubilize metals like gold and platinum. Very, very important with respect to your exam point of view. Fine. So now along with that, we have discussed about chlorine, right? So along with these things, we have discussed about the chlorine. Now, when I am talking about chlorine, so chlorine is a very good bleaching agent. Chlorine is a very good bleaching agent, right? So that's where we have discussed. Now, when I am talking about chlorine, what should be a good bleaching agent? That is because when chlorine water, when we have the chlorine water, slowly it gets converted into HCl and HOCl, hypochlorous acid, right? So whatever hypochlorous acid is there, it will get converted into HCl and there will be release of nascent oxygen. There will be release of nascent oxygen. So due to that, chlorine is a very good bleaching agent. And due to this reaction, first one, chlorine is going to lose its yellow color, especially chlorine water is going to lose its yellowish green color because slowly it will get reacts with water to form HCl and HOCl. Fine? All of you will agree? So that's what we have discussed. Now I think yesterday I have forgotten one of the method for the preparation of chlorine, I think I have forgotten to discuss that one, that is related to Decon's process. Preparation of chlorine, I think I have left with the Decon's process. Any one of you can tell me the reaction? Because that one we have discussed in some other chapter. Okay? Any one of you can tell me what you mean by Decon's process? We have discussed this one actually. Decon's process, and I told this is bit important. I think this one I have not discussed in the last class, right? So I can mention this one as important. Somehow I have forgotten. So that's where we have the Decon's process for preparation of chlorine, where HCl will be treated with oxygen. HCl will be treated with oxygen to form chlorine and water. To form chlorine and water. So we have to balance it, right? 2H2O, 4HCl, 2Cl. Yes. So that's where we have the reaction. Reaction of preparation of chlorine, that is Decon's process. Okay, and it will be done in the presence of cupric chloride, CuCl2. Fine. So this is bit important. Anyway, this reaction we have discussed. Where? With respect to the oxygen. To tell that, with respect to the oxygen we have discussed, to tell that it's an oxidizing agent. To prove that oxygen is a oxidizing agent. During that time we have discussed this reaction where 0 minus 1, but here chlorine is becoming 0 and oxygen is becoming minus 2. That shows that oxygen is more electronegative compared to chlorine, right? So that's what Decon's process. Fine. So these are the things, some of the reactions which we have discussed in the previous class. Fine. Any doubts? Any doubts related to this one? Okay, in that case, we will move to the next one, that is group 18. Okay, another thing here is what I saw at the end in text question they have given about the fluorinating property that we have discussed with respect to O2F as an example. Right? Same thing can be done for uranium also, because when it comes to uranium, we have uranium 235 and 238. There are many, but when it comes to uranium, we have two types. Uranium 235 and uranium 238. Now, uranium 235 is going to very helpful with respect to its radioactivity even at low temperature. So that's why it can undergo for fission reaction. So during the purification of these two, where I want to take out uranium 235 from 238, during that time also they will go for fluorination, where they will use halides with respect to fluorine with respect to other halogens like CLF and all. Right? So during that time also they can use this particular fluorination property. They will apply this particular fluorination property. Fine. For example, if I take uranium, so when it is treated with CLF3, it will get converted into uranium hexafluoride. So it will get converted into uranium hexafluoride. What should be the another product? What should be the another product? It will be CLF. Further, if you make it, chlorine will be liberated. So that's where we have 7. So in that case, what I should do is I will make it as 2 so that it will become 8. So even 8 is not possible. Even 8 is not possible. I will make it as 3. Then almost 1 by 2, then 3. Then here also it should become second. Fine. So that's where we have the fluorination property of interhalogen compound. This is related to interhalogen compound. So we have discussed fluorination property with respect to O2F2. So this is with respect to interhalogen compound, one of the application where they want to separate different isotopes of uranium. That's what I told, right? So where they want to separate different isotopes of uranium, that's where they will go for this reaction. And since there will be difference in the mass of uranium hexafluoride with respect to different isotopes, they can be easily separated. Fine. So that's where one of the application of interhalogen compound in that related to fluorine. Interhalogen compound where one of the partners should be fluorine. So which can be used as a fluorinating agent. Fine. Any doubt? Okay. So we will move to the last part of the topic, that is called as, that is group 18 elements. We are coming to the last part of the topic, that is nothing but group 18 elements. Now when I am talking about group 18, all of us we know they are having inert gases. They are having inert gases, 0th group element, right? So that's where we have the group 18 elements. So which are composed of inert gas. Now when I am talking about inert gas, that shows that they are least reactive. That's why they are called as inert, right? Now in this we have helium, neon, argon, krypton, xenon and radon. That's where we have the group 18 elements. Now if I want to write the atomic number, then helium is 2, add 8 to this, then it will become 10, add 8 to this, then it will become 18, add 18 to this, then it will become 36, add 18 to this, then it will become 54, add 32 to this, then it will become 86. That's where we have the atomic number. That means 8, 8, 18, 18 and 30. Because it starts from period number 1. So therefore the difference will be here will be 8, 8, 18, 18, 32. Since it will start from period number 1. So that's where we have the group 18 elements. Fine. Now very important point here is, okay fine, before that we will write the electronic configuration also. Now when it comes to helium, it will be 1s2. It will be 1s2. Now when it comes to neon, you can take the help of helium then. Now we can write it as helium and then what else? It will be 2s2, 2p6. 2s2, 2p6. Now next one is argon. So when it comes to argon, here it will be neon in this square bracket. Then we can write it as 3s2, 3p6. Then we can write it as 3s2, 3p6. So if you are having confusion, then on one side you can write the off-go diagram. That's where 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, 6s, 6p, 6d, 6f. So 1s will get filled up, then 2s, then 2p, 3s, then 3p, 4s, then 3d, 4p, 5s. So like that electron will be filled up. Fine. Now next one is krypton. So we can take the help of argon. So 18. The difference of 18, right? So that means when I am written argon in the square bracket, then up to 3p6 we have done. That means here up to 3p6 we have done. Then we have to go with 4s2, 3d10, 4p6. Right? So that is related to krypton. Then when it comes to xenon, we can take the help of krypton. So krypton means I have written up to 4p6. 4th period, right? So I have written up to 4p6. Then I have to write 5s2, 4d10, then 5p6. Then the last one, radon. I can take the help of xenon. So where I can write the xenon. So xenon belongs to 5th period. That means 5p6. Just now we have written. That means after 5p6, 6s2, 4f14, 5d10 and 6p6. Right? This is where we have the electronic configuration for inert gas. That's where we have the electronic configurations for inert gases. Fine? Now therefore, in general, except helium, all of them, they have this type of outer electronic configuration. All of them, they have the electronic configuration of this type. That's where we have the electronic configuration. Okay, that means outer electronic configuration except helium. For all the others it will be NS2, NP6. NS2, NP6 except helium. Okay, so that's where we have the NS2, NP6. That means they are already in the octet state. They are already in the octet state. Right? So that will make them inert. Since they are already in the octet state, that will make them inert. That means this will make them to have very less reaction or least reactive in the periodic table. So that is the reason. Right? So that's where we have the inert gas. Fine? So why they are inert in nature? Major point here is they are in the octet state. Fine? Since they are in the octet state, please remember, I told whenever it comes to electron gain enthalpy, always it will be with negative value. I told, right? Other than the inert gas. Inert gases are the one which will have positive electron gain enthalpy. They will have positive electron gain enthalpy. That means most of the element in the nature, in the periodic table, they have the negative electron gain enthalpy. That means whenever electron is added to them, there will be release of energy. That's what in thermodynamics negative sign indicates, right? So whenever there will be addition of electron, so that will lead to the liberation of energy. So that's where they will be having negative electron gain enthalpy, amount of energy released when electron is added to the atom. But in this case it is positive. That means they will not going to accept the electron easily. So that's where it is having the positive electron gain enthalpy. So that is because they are already in octet state. They don't want any other electron. They don't want to share with any of the element, any electron. So that is the reason. Same thing, octet state can also lead to very high ionization enthalpy. It will lead to very high ionization enthalpy. Very high ionization enthalpy. So now we can tell. So due to the positive electron gain enthalpy and due to very high ionization enthalpy, inert gases are least reactive. Our group 18 elements are least reactive. So why they have positive electron gain enthalpy? Due to the octet state. Why they have very high ionization enthalpy? Due to the octet state. Fine. Now, same reason, due to the octet state, they will be present as monoatomic form. They will be present as monoatomic form. If you recollect, in first PU, you had one molecular orbital theory, MOT, where we have disproved that existence of helium in diatomic form. We have disproved by using MOT, molecular orbital theory, if you recollect. So that's why when it comes to inert gas, they are the element which will be in monoatomic condition. Why they are in monoatomic condition? That is already they are in octet state. Say for example, if I take chlorine, group 17 elements will be in diatomic form, right? They will be present as diatomic form. So why they will be present as a diatomic form? Because they have one electron which will be shared with another one. That's where they can attain the octet state. So therefore group 17 elements will be in a diatomic form because they have shortage of one electron. But when it comes to inert gas, already they are in octet state, they will prefer to remain in monoatomic state. Fine. So one point can decide so many properties, right? So octet state, it will lead to monoatomic form of inert gas. Octet state, it will lead to positive electron gain enthalpy. Octet state, it will lead to very high ionization enthalpy. And all these reasons, not monoatomic, all these reasons are the one which can be answered for their inertness, least reactiveness. Okay? So any doubts? Any doubts? Okay. Now, when it comes to physical form, physical state of these elements, naturally in the name itself it is there. All of them, they will be present in gaseous state. All of them, they will be present in gaseous state at room temperature. They will be present as gaseous state. So when I am talking about gaseous state, now question will be, why inert gas will be in gaseous form at room temperature? Right? Say for example, if I take helium, which is having the least boiling point present in the nature. Helium is the one which is having
biology class today 10 p.m. June.
Hello students.
Biology class today at 10 a.m.
Biology class will be there at 10 a.m. today.
They will get the Zoom link.
And you will be having Zoom link. You will get that one. Fine. So once again I will explain. Biology class will be at 10 a.m. and you will be having or you will be getting Zoom link very soon. Whether I am clear?
And we can take up to 9:15.
Fine. So any doubts? So biology class will be there at 10 a.m. and for that it will be Zoom link will be sent to you. Okay, we'll come back to the class. So when I am talking about inert gas, that's what I was telling that why they will be present in gaseous state, right? So now when I am talking about helium, helium is considered as one of the element in the nature which is having lowest boiling point, somewhere around 4.2 Kelvin. So if I want to convert into degree Celsius, always we will go with degree Celsius. So when I am converting it to degree Celsius, I think it may be somewhere around approximately I am telling 270 or 273 degrees Celsius. Can you imagine? minus 273, sorry, minus 273 degrees Celsius, very, very low, right? Very, very low temperature. We cannot imagine at all. So liquid nitrogen somewhere around minus 196, minus 196 degrees Celsius. If I take liquid nitrogen, but here it is minus 273, right? So that's where we have the inert gas, which will be present as a gaseous molecule at room temperature. Okay. So with regard to computer science, okay, this was the announcement. So computer science will let you know. Okay. So that's where we have the temperature. So any doubts? That is with respect to inert gas. Now the question here is, why they have such a low melting point, or why they have such a low boiling point, or why they are present in a gaseous state at room temperature? The answer will be due to least interatomic interaction. Interatomic interaction, because they are not present as a molecule, they are present as a monoatomic state, right? So therefore, due to the least interatomic interaction, or I can tell, since they are monoatomic, there is no question of dipolar interaction, there is no question, then there is no question of hydrogen bond, so only left over will be weak van der Waals interaction or dispersion force, London dispersion force, very weak dispersion force will be there. So due to that, they will be having low boiling point or melting point. Fine. So if someone asks you why inert gases they have the low melting point or boiling point, then you can tell that they are present in the nature as a monoatomic form, and they will be having least interaction among themselves. Fine. So they are liquefied at very low temperature, hence they have low boiling point. Okay, fine. So that is actually what you have written. They are liquefied at very low temperature, therefore they have low boiling point. That is fine. That is the result because of some reason. The reason is why they are liquefied at very low temperature. Now that will be the question now, right? So instead of writing that, you can tell that since they are present in monoatomic form, and since there will be least interaction, so therefore they will be having low boiling point. Even you can tell that one, no problem. You can even tell that one also, because they will be present as a liquid at very, very low temperature. So definitely in that case they should have the low boiling point, no doubt. Fine. So but I want this particular word, interatomic interaction, least interatomic interaction. Fine. Since they are in monoatomic form. Any doubts? Oh, I removed this. Okay, fine. When it comes to inert gases, based on their reactiveness, we can write or we can classify inert gas as reactive and least reactive. Fine. So whatever inert gases which are present at the top, like helium, neon, argon, we can consider them as least reactive. Please remember, all the inert gases are least reactive, but among the inert gas I am telling, they are least reactive. Then once this is done, krypton, xenon and radon. Anyway, radon we are not going to consider. So that's where we have the reactive inert gases, slightly reactive inert gases. So why I am not considering radon? Because radon is radioactive. Radon is a radioactive element. Fine. So that's where we have the one of the inert gas which is radioactive element. And due to that, they occurs very less in the nature, least occurring inert gas in the atmosphere. That is radon in the nature, not in atmosphere, in the nature. Least occurring element. So this is what? One more question I think they had asked. So least occurring in nature. Least occurring in nature. Which is that one? That is nothing but radon. And to some extent, once radon, even xenon can belong to the same category. Least occurring in nature. But radon is much more less compared to xenon. Fine? So please remember, all the inert gases are non-reactive, very, very less reactive, no doubt. But if I take the inert gas, I can tell that they are much more less reactive among the inert gas, and these three are, especially these two are bit reactive. Whether I am clear? All of you have understood? Okay? So that's where we have the inert gas, and among that radon is radioactive, and because of its radioactivity, radon is least occurring in nature, but sometimes even xenon they will include in this category, less occurring in nature. Fine? That might be due to xenon is bit reactive. That might be the reason why they are not present freely in the nature as that of other inert gases. But radon is radioactive, and they will tell that radon is present in the nature due to the radioactive decay of radium. Radon is present in the nature due to the radioactive decay of radium. Okay? So where it will get converted into radon 222 and 86. And there will be liberation of alpha radiation. There will be alpha. Helium nucleus will be emitted, alpha radiation. So whatever radon is present in the nature, it is resulted due to radioactive decay of radium. Fine? So therefore they are least occurring in nature. So due to these reasons, they are least occurring in nature. I don't think anything I have left. Fine? Any doubts in this? Okay. So later, a person called as Neil Bartlett, he is the one who identified existence of these compounds which are having inert gas as their component. So Neil Bartlett is the one who prepared inert gas containing compound. So person name is Neil Bartlett, and from there we came to know that some of the inert gas compounds are existing in the nature. They are present in the nature. And very important point here is most of the inert gas compounds are with respect to highly electronegative element. Most of the inert gas compounds are with related to highly electronegative element. Can you tell me which can be those? Highly electronegative elements I am telling, not element. Neil Bartlett is the one who first synthesized inert gas containing compound, no doubt. But later we came to know that inert gas can make the compound with most electronegative elements. Can you give the examples for that? Okay, Mayank is telling halogen. But in halogen all are not very inert electronegative. So normally yes, it is oxygen and fluorine. Most of the inert gas compounds are having, or it is with oxygen and fluorine. Fine? Yes, Banu. That is Bhavani. That is oxygen and fluorine. Fine. So that's where we have the inert gas compounds. Okay. Fine. So even whatever he has synthesized, even that one was actually xenon platinum hexafluoride. Xenon platinum hexafluoride. Xenon platinum hexafluoride. That was the one who first synthesized. So xenon platinum hexafluoride. Fine. This was ionic compound. This was a ionic compound. But anyway, now we have lots and lots of reaction where we can have xenon with fluorine. Many compounds are there. Fine. See, for example, if I take xenon, if I treat the xenon with fluorine, molecule will be xenon difluoride. Okay. So when I am having xenon, when it is treated with fluorine, then I will be having xenon difluoride. Same way, if I take the xenon, when it is treated with fluorine, we are going to balance the equation. Xenon tetrafluoride. Same way, when I am talking about xenon, when it is treated with fluorine, then it will be xenon hexafluoride. So xenon difluoride, xenon tetrafluoride, and xenon hexafluoride. So different compounds of xenon fluorides we are going to get. Now in this case, when I am talking about xenon fluoride, so temperature will be somewhere around 870 Kelvin and 1 bar pressure. 870 Kelvin and 1 bar pressure. Please remember, all of them, they are in the solid state. So then on xenon and fluorine, so we have to balance it, 2F2, okay. So temperature will be somewhere around, okay, I think 870 Kelvin should be here. 7 bar pressure, where it should be 470. Okay. So then when it comes to here, it will be 3F2. So where we will be having around 570 Kelvin and 60 bar pressure. Fine. So 470, 870, 570. I have rounded it off, temperatures and all. Okay. So that's where we have the xenon difluoride, xenon tetrafluoride, and xenon hexafluoride. Now if I observe here in this case, it looks like they are 1:1 ratio, but in reality they will be taking xenon in excess. This will be done when xenon is in excess. But based on the equation we can tell that they are in 1:1 ratio, but in reality xenon will be in high concentration compared to fluorine. But stoichiometric equation, it looks like 1:1. Fine. Now when it comes to here, it looks like 1:2, but in reality they are in 1:5 ratio. Concentration wise I am telling 1:5 ratio. Please remember, I am not talking about ratio in stoichiometric equation. I am talking about ratio with respect to their concentration. So it looks like 1:5. Now same way here, it is somewhere around 1:20. 1:20 ratio. So that's where we have the reaction. Now if you observe, everywhere they have used pressure. 1 bar, 7 bar, or 60 to 70 bar. So what might be the reason? What might be the reason why they are applying the pressure?
So because electron gain on value.
No. make it as 670. First one you can make it as 670. Okay, anyone? Why pressure has been applied in all the reactions? I have given a hint actually in the equation itself. Okay, so what is the physical state of xenon? Okay, they are powerful. Bhavani, no, they are not powerful, so not because of that. The reason here is all of us we know they are gas, and fluorine definitely they will also present in the gaseous state. So same logic, since reactants are gaseous in nature and products are solid in nature. So if you apply the pressure, what will happen? It will move towards the forward direction. Okay, so that is the reason. Any doubts? All of you have understood? Same way, we can even synthesize xenon fluoride by using another compound. Can anyone of you tell me which is a very good fluorinating agent? Which is a very good fluorinating agent? Anyone of you can tell me which is that? ClF3 he is telling, Mayank, but anyways, not ClF3. That one we have discussed about that compound as fluorinating agent only. AgF, no. It is dioxygen difluoride. If you recollect, we have discussed this can be used as a fluorinating agent. That's why one of the another application where it can react with Xenon Tetrafluoride. It can react with, someone had written, it can react with, no Bhavani, not XeF2. So it is Xenon Tetrafluoride can react with dioxygen difluoride to form XeF6 plus oxygen. XeF6 plus oxygen. That's where we have another application. One of the application of oxygen fluoride, dioxygen difluoride we have discussed. Which is that? Where we have discussed. That was related to nuclear spent fluid. That's where we used to isolate one of the radioactive element. Which is that one? Any one of you? Dioxygen difluoride as the fluorinating agent we have discussed for the treatment of nuclear spent fluid, where one of the element will be purified or will be isolated, which can be reutilized for some other purpose. So which is that one? I will give a hint. It will start, symbol will start with P. Anyone? What I love. Not reading. Not PI. No. That is plutonium. Pu. Right? So that's what we have discussed. Pu. Not PO. Polonium agbidutte. PO andre. Plutonium. Pu. So that's what we have discussed as one of the application of oxygen, dioxygen, difluoride. Fine? And this is another example where we can prove that O2F2 is acting as a fluorinating agent. This is another example. Another way of preparing the xenon hexafluoride. Fine? All of you have understood? Now whatever I will be telling, that is very, very important for your exam point of view. Please remember, there were question on this group 18. 1 mark question was like, name the inert gas which is less occurring in nature. 1 mark question, that is radon. Then name the radioactive element among the inert gas, that is radium. Sorry, that is radium. Sorry, radon, that is radon. So that will be another question. So like that they have asked for 1 mark. But when it comes to reaction from this particular part, that's what I am going to write here. That will be the important reaction you can expect for your exam. Fine? So that's where we have the reaction of these fluorides. Reactions of these fluorides means inert gas, related to inert gas fluorides with water. With water. Right? So now in that first one will be XeF2. First one will be XeF2. Now when XeF2 is treated with water, XeF2 is treated with water. Now the product will be xenon, hydrogen fluoride and oxygen. Xenon, hydrogen fluoride and oxygen. Balance the equation. First, xenon. Okay, I will make it as well, so I think it is easy. So because it is 2, so then it will become 4HF. So it will become 2. Balanced. Okay, so that's where one reaction. So xenon difluoride with water will form xenon, hydrogen fluoride and oxygen. Next, XeF4 with water. XeF4 with water. Now all the products will be same, but in addition to that there will be xenon trioxide. I told inert gas will make the compound with highly electronegative element. So one of the examples, xenon trioxide plus xenon hydrogen fluoride plus oxygen. We can balance the equation. So all are important reactions. So first we will go with fluorine. Okay, here we will make it as 4HF. For time being, don't write anything. Less occurring is fluorine. So first we are going with fluorine. Then, okay, no. Fluorine is not going to work out because we have xenon as 2 molecules here. So we have to make it as 2XeF4. Then here it will become 8 hydrogen fluoride. So here it will become 4 H2O. But there it will be 5, oxygen will be 5. No, it will not work out with these numbers. It's not going to work out. So instead of that, we can make it as, since pure xenon is there, so we will go to the next one. Don't write anything.
So HF you can make 16 and here 4 for xenon.
Balance, na? It is balanced. Okay, done. It is balanced. And then you can go 6 here and no, it's not possible. Okay. So this is one reaction. That is xenon tetrafluoride. So next one will be xenon hexafluoride. Now that's where you can see one difference in these two. What is that difference? When it comes to xenon tetrafluoride, XeO3 will be formed, but all the other products are same. So we have to remember about XeO3, which differs it from first reaction. Now when it comes to xenon hexafluoride, now we are going to have XeO3 and hydrogen fluoride, that's all. So there is no Xe and oxygen when it comes to xenon hexafluoride. So when it comes to xenon hexafluoride, so we don't have the xenon and oxygen. So that's where you should remember. So these are common with respect to tetrafluoride and hexafluoride. That is xenon trioxide. They are common, right? Even hydrogen fluoride is common, but xenon and oxygen is not present with respect to hexafluoride. Now we will balance it. So 3. So straight away we will make it as 3 here. Now in that case, we will, okay, I think it will be balanced. Okay, done. So that's where we have the reaction. Whether I am clear? So what I am telling here is all the reaction that is with respect to complete hydrolysis. Whatever reaction I have written, it is related to complete hydrolysis. So xenon difluoride, it will give rise to xenon hydrogen fluoride and oxygen. Xenon tetrafluoride, it will give rise to xenon trioxide, xenon hydrogen fluoride and oxygen. And xenon hexafluoride, it will give rise to xenon trioxide and hydrogen fluoride. Whether I am clear? So common with respect to tetrafluoride and hexafluoride is xenon trioxide and hydrogen fluoride. Common with respect to difluoride and tetrafluoride is xenon hydrogen fluoride oxygen, xenon hydrogen fluoride and oxygen. So whether I am clear? Okay. Now when it comes to xenon hexafluoride, even this one they had asked. Even with respect to xenon hexafluoride, it can undergo for partial or incomplete hydrolysis. It can undergo for incomplete hydrolysis. So now whenever XeF6 will undergo for incomplete hydrolysis, in your textbook I think they have given it as two different equations. I am combining that two equations. So it will give rise to XeO2 F2 plus XeOF4 plus hydrogen fluoride. So that means xenon dioxyfluoride, xenon dioxydifluoride. Here it is xenon oxytetrafluoride. So what is this? Xenon dioxydifluoride, and this is xenon oxytetrafluoride. Fine. So these are the products. So we will balance the equation. So fluorine is balanced. Xenon, okay, xenon is not balanced. Or even fluorine is also not balanced. So what I will do is I will make it as 2 to make xenon equal. So now 16. So already 6 are there. In that case I should make it as oxygen is 3, right? So I will make it as 3 here. Now here I should make it as 6. Yes, it is balanced. So that's where we have the incomplete hydrolysis of xenon hexafluoride.
It seems we are running middle classes, there are 9.
Means
9,
second page.
No.
Okay. Even they didn't tell. 1 minute. Sure, no sir?
Yeah.
Because no one has told anything.
No. You can close as quickly as possible.
Okay. So, no, but biology class.
Please reschedule to 10:30. That also you can tell. 10:30.
Okay. So one small correction is that, so I made an announcement that at 10 o'clock we will be having biology class, but it has been rescheduled to 10:30. And I think 9 o'clock we have madam's class, Liverani madam's class. Fine. Whether I am clear, at 9 o'clock we will be having Liverani madam's class, and at 10:30 biology class. It has been rescheduled to 10:30 from 10. Okay. So that's where we have the incomplete hydrolysis. Okay. Now we have to go with the geometry. In that case I should be a bit fast. So if I want to go with the geometry, xenon trioxide. Xenon trioxide is explosive. Please remember, xenon trioxide is explosive in nature, like nitrogen trichloride, NCl3. They are explosive. Now when it comes to xenon trioxide, can anyone of you tell me what should be the geometry? First thing, what is the hybridization? Oxygen, lone pair of electrons.
sp3.
It will be sp3 hybridization, right? So now what is the geometry? It's like ammonia. It's like ammonia only, right? So where NH3, one lone pair of electron. So trigonal pyramidal structure. So it will be having trigonal pyramidal structure. Please remember, even this one they had asked. The question was, if I am right, the question was, what name the geometry of the product which is formed when partial hydrolysis of xenon hexafluoride will take place. So that was the question. Okay, na? Okay, sorry, it's not trigonal, it's simply pyramidal structure. Trigonal means we should have this one. Okay, fine. You can simply write it as pyramidal structure, just like ammonia. So you can mention it as pyramidal. So next one is xenon hexafluoride. Xenon hexafluoride. So 1, 2. Can anyone tell me xenon hexafluoride? Can anyone of you? Xenon hexafluoride, first. So 1, 2, 3, 4, 5, 6, 7. So total 7. So sp3 we have done with the 4. So further we require 3. So sp3 d3 hybridization, right? Xenon hexafluoride sp3 d3. What is the shape? If I take only 6, then it would have been octahedral. But since there is the presence of lone pair of electron, we can call it as distorted octahedral geometry. Don't write simply as octahedral. It is not simply as octahedral. It is distorted octahedral structure. Distorted octahedral structure. Fine. So this is with respect to xenon hexafluoride. Now next, when it comes to xenon tetrafluoride. Xenon tetrafluoride. So whatever lone pair, they will be far. They will occupy the equatorial, axial position. And all the fluorine, they will occupy the equatorial position. It will be, any one of you?
Square bipyramidal.
It's not bipyramidal, it will be square planar. Sorry. It will be square planar because it will cancel each other. So it will be square planar. So lone pair of electron equal and opposite, right? So they will be cancelled. So it will be square planar structure. It will form square planar. It will cancel. Okay. So whatever is there is equal and opposite will cancel. So that's where. Oh, what is the geometry? What is the geometry of XeF geometry? Hybridization of XeF4. I am a bit fast because I came to know that we have 9 o'clock class. What is the geometry there? sp3d2 hybridization. sp3d2 hybridization. This is for XeF4. When it comes to XeF6, sp3d3 hybridization. Now XeF2. Can you tell me XeF2? So whatever fluorine, it will be here and they will occupy the position here. So it will have the linear structure. It will have the linear structure, XeF2. Right? It will have the linear structure, XeF2. So what is the hybridization? Fast. sp3d. 1, 2, 3, 4, 5. So sp3d. So this is XeF2. sp3d. Now what about what is left over? XeO2F2. XeO2F2. Fast. XeO2F2. XeO2. Okay. So which type of geometry? Fast. Which type of geometry? This one we have discussed already. By the help of SF4, sulfur tetrafluoride, we have discussed. See?
Seesaw.
It will be having seesaw structure. It will be having seesaw structure. What is the hybridization? 2, 3, 4, 5. So 1, 2, 3, 4, 5. So what is the hybridization? sp3d. Right? sp3d hybridization. Last one, XeOF4. XeOF4. Fast. It will be Xe, fluorine, oxygen, so lone pair. What is the geometry?
Square pyramid.
It will be square pyramid. Hybridization, XeOF4, hybridization. It will be 1, 2, 3, 4, 5 and 6. So sp3d2. Fine. So you have to remember this one. So it is sp3d2. So you have to remember all these things, geometric shape and hybridization. Fine. Now I will come to last one sentence. Okay. So that is when I am talking about helium, due to its inertness, it will be utilized as a diluent. It will be used as a diluent with respect to oxygen supply. Hospital oxygen hakirtaralva. So don't think that it will be pure oxygen. Pure oxygen kottbitre manusha negadu bidogtane badakadalla. Okay? So it will be diluted. It will be diluted with helium. And the same way, whoever is going for deep diving in the ocean, so they will carry the oxygen cylinders, right? So don't think that it will be pure oxygen. Once again, it should be diluted with 1 minute upper. Done. I will be finishing. So that's where we have the helium, which will be used as a diluent. Why helium will be used as a diluent? Because of its inertness and light weight. Because of its inertness and light weight, it will be used. Even in the balloon, to send it to top, up in the atmosphere, above the atmosphere, that's why they will be putting helium in the balloon. Fine? So anyway, so it was a bit fast. So I will stop here. So I think already your Zoom class is going on. Take care. Bye. We are starting with alcohol tomorrow. So P block is done. We have finished. Take care. Bye.